All right. So let's just go ahead and have a review from the beginning. Remember, the first part of class we talked about pretty much how the ocean floor was made and everything about the sea floor. And now we're talking about the water in the ocean and what the water is like. So you should be able to draw a water molecule and know that the oxygen is -2 and the hydrogens are each -1, and that it is an asymmetrical molecule. Water is an asymmetrical molecule, and one side's positive, the other side's negative, and because one side is positive and one side is negative, it's called a polar molecule. You should be able to draw it. Water has high heat capacity, which means it doesn't like to change temperature. And I know I put up the heat capacity movie that was made by JPL, NASA. I know I put that on the website. I will put it up for you again in this week. So you can watch it. And we did make a movie last semester that many of you guys have seen on heat capacity, but I will not put that one up because it's mine and I don't want to give it away. But water has very high heat capacity, which means water doesn't like to change temperature. Water likes to stay the same temperature. It takes a long time to heat water. It takes a long time to cool water down. So what that means, what does that mean for me? Well, yeah, it means that it takes a long time to cook soup compared to toast, and that your soup stays hot a lot longer than your toast. That's one thing. But it also means that because the earth has so much water on it, that we have a mild climate here on planet Earth compared to other areas that don't have water on them. So the moon, Mars, other places that don't have water have extremes. They get really, really, really hot when the sun is on them and freezing, freezing cold when there's no sun. So in the winter or the nighttime, Mars, moon, areas like that have extremes in temperature, impossible to live there, where the ocean makes our climate on Earth more mild. Additionally, the closer you are to the ocean, the more mild the climate is. So if you live in a coastal region, you have a mild climate. You've got mild winters, mild summers, compared to inland, like the middle of the country, where you get much more extremes. You get it freezing cold in the winter and burning hot in the summer. So you've got more extremes in temperature than you do living in a coastal region. And the name for areas that are close to the coast is called a maritime climate. Maritime climate. I'm sure I wrote that on the board when I saw you, but I'm telling you verbally now. Maritime climate, living close to the coast. Other things we talked about this section of the class is that the ocean is density stratified, as is, remember last time we found out that the whole planet is density stratified. Well, the ocean is density stratified too. So there's a deep zone with the deeper, heavier water, and that's about 80% of the water is in this deep zone where it's cold and it's dark. And then there's the surface water, which gets the sun and it's warmer. And then you've got this area of change where it slowly gets more dense, and that's called the pycnocline, this change in density. So the surface water, which is warmer, doesn't want to sink to the bottom because warm things float and cold things sink. So the cold water tends to stay on the bottom. It has no reason to move up to the top. The heat, the source of the heat, is at the surface from the sun, so that's where the water gets warmed, and it tends to want to stay on the water. So the ocean is not very well mixed. You get a surface layer, a deep zone, and it takes like over 1,000 years for them to mix. So here you've got your pycnocline. There, you also learned about a thermocline, and that's because I really do need to get the cat now. Okay. So the one cat was scratching at the door, but the other cat was scratching at the door on the other side, and this cat, say hi to everybody, scared the other cat away. So now we know we have cat action. Hello, yes, okay. Oy. Now the cat's climbing all over me. Ow! Jesus Christ. Oh, kitty! Okay, cat clawed my shirt, not me. Okay, the thermocline. So notice this is temperature right here, okay? So this is higher temperature, this is warmer, and it gets gradually colder. Come here, mouse. Gets gradually colder as you go down, right? So here, can you see here's depth right here? 0 meters is the surface, 1 kilometer or 1,000 meters, 2 kilometers, 2,000 meters, etc. 3 kilometers, 3,000 meters. And you know the ocean, the average depth is 4,000 meters. So that's why it goes 4,000 meters down. And here you've got feet, I guess, on this side. Who cares about feet? Anyway, so you see here's cold and here's warm. Cold and warm. So it's warmer at the surface because that's where the heat is. And then the water gradually gets colder as you get deeper. So at the surface, you've got a thermocline, or at the surface, you've got a surface zone that's warm, then this intermediate layer, a thermocline, which is a change in temperature with depth, and then the cold zone all the way at the bottom. And remember, I asked you to be able to draw the 3 types of thermoclines, right? Tropical, temperate, and polar. You should be able to draw 3 types of thermoclines and label them. And here's your standard thermocline, which is kind of a better drawing than that one. So you should be able to draw this graph like this, and a 0 and your kilometers. Please use kilometers. And here's your temperature in degrees C across the top. So if I put a thermometer at the surface, average around the world would be about 17 degrees C. And if I put it down, 10 meters, 20 meters, about to 100 meters, it would stay at about 17 degrees C. But then once I put that thermometer deeper, it starts to get colder. So if let's say I put the thermometer down to 500 meters, I would find out that it was 10 degrees C. And if I put the thermometer down at about 1,000 meters, it would be about 5 degrees, and colder and colder and colder and colder. So it gets about 2 degrees is as cold as it is here in the dark. And this area is this whole thing is called the thermocline graph. But here's your surface zone, your thermocline area, and then your deep zone. Okay? So the thermocline just means a change in temperature with depth. And then here's your 3, and on this graph they're kind of written on top of each other. If you have colored pencils and you're really good at labeling, it's on the test for sure. I'm going to ask you to draw and label the 3 types of thermoclines. You will get 100% on that question if you have different colors, but I've noticed that when people try to draw them on top of each other and they don't have fancy colored pens, then it's really hard to see which one's which, and sometimes I have to take points off because it's a mess. So I recommend drawing 3, which I've done for you in class. The polar one, there's still a thermocline. It still gets colder. It just starts out at about 5 degrees and then goes down to about 2. The temperate one is here in green, starts out about 17, it's the average, and then here you go in the tropics where it's warmer, the surface temperature is about 25 degrees, and then of course it's really steep, the thermocline here, because there's all that hot water at the top, but then as soon as you get a little deeper it's cold. And you'll notice if you were in a submarine 2,000 meters deep and all you had was a thermometer, you wouldn't know if you were in a submarine under the North Pole or if you were in a submarine under the equator, because it's about 2 degrees and dark about 2,000 meters down, so you wouldn't know. So only on the surface is the ocean water different temperature. And the reason why that is because here you get the surface light coming in. At the surface, all these different colors and all this different energy of light is coming in, but only 1 meter down, more than half of that light is already absorbed, and all the red is absorbed out. 10 meters down, a lot of it is absorbed, just this little bump, and 100 meters down, only 1% of light penetrates. 99% of the light has been absorbed in the top 100 meters. And when it gets absorbed, not only is there no more light that passes through, but also that absorbing of the light heats up the top 100 meters or so. And that's about it. Absorbs all the colors except blue is the 1% that can pass below 100 meters, but even still not that far. And here's your old-fashioned view of sea surface temperatures. This warmer water around the tropics, colder water in the poles. Here's the other cat again. Come on, don't fight, you guys. Come on. Get in here. Don't fuck up. Here's the other one. Now this one doesn't scratch because he's not a rescue. He's a lover. Are you a lover? Okay. The polar area, colder, around between 0 and 5 degrees or so. And then the temperate area where we are, about, 15 to 20 degrees, so average 17 degrees. And these are sea surface temperatures. And then when you go on the website climate.nasa.gov, when you're going to vote for the Webby Award for me, and also when you're going to study for this class, which you can definitely study for this class on that website, you can look at the sea level viewer, and you can see, and you can also look at the ocean satellites, and you can see a much more modern view of what the ocean looks like from space. You can see the sea surface temperatures from space. I'll probably put that up there too. I'll get some stuff for you from the website, and so you can see the sea surface temperatures from space in a more modern looking view. Okay, so what else about water? We've looked at the temperature of water, or the high heat capacity of water, and now we're going to look at the fact that water dissolves salt. So why does water dissolve salt so well? Well, because it's a polar molecule. It has the positive sides. The hydrogen side is attracted to the negative chlorine ion, and the negative side, the oxygen side, is attracted to the positive sodium ion. So that's why here's your salt, and a salt is just two ions attracted together. So chloride is negative, sodium is positive. That's why these stick together. But then once a salt molecule gets into water, the water is able to dissolve it because the negatives surround the positive, and the positives surround the negative, and then it's a dissolved salt. And that's why so water is a fantastic at dissolving things because it's a polar molecule. The other thing about the ocean water is that, and this is kind of what I want you to remember for the test, and that is that water has constant proportion, right? The saltiness of the water is constant proportion. The most abundant is chloride, and the second most abundant is sodium, and then all these others, which I'm not going to ask you to remember, but I want you to remember that doesn't change. You won't find any places in the ocean where there's, here's a whole bunch of potassium, or in this place there's a whole bunch of magnesium and not very much chloride. No, it's always in this ratio. Always in this ratio. Always this amount of pi is chloride, this amount of pi is sodium, this amount of pi is sulfate, etc., and all the way down. So it's a constant, that part. The other thing is that the amount of salt in the water varies, and that depends on how much evaporation or precipitation you have. So when there's a lot of evaporation, really the salt is staying the same. A lot of evaporation takes the water out, so there's more salt left in the water, so the water is more salty. When there's a lot of precipitation, there's water added to the ocean, there's water added to the seawater, so the ocean gets less salty. Again, the salt is staying there, it's just the water is going in and out depending on if it's very dry, it'll be more salty, or if it's very rainy, it'll be less salty. So salinity depends on whether or not it's rainy or dry, not on what kind of salts there are. The proportion of the salt is just sitting there in the ocean staying the same. So here's your old-fashioned view of salinity, and as I mentioned, they're launching a satellite, I think, this summer to look at salinity from space, so we'll have newer ones of this. But you see where the Atlantic is a little bit saltier, the Pacific is a little less salty, places where it rains a lot. Here you've got the subtropical rainforests over here, less salty. Here you've got the reason why this is salty here, this is the Sahara Desert. The biggest desert on the planet is right here, and winds are blowing both ways. So this is why you've got more evaporation here and more salty areas, because you got a huge desert, not so much rain. Lots of rain over here, so it's a little less salty. But you'll notice that salinity doesn't vary very much. The least salty it gets is about 33 parts per million. Or, I'm sorry, 33 parts per thousand is the least salty it gets after a rain, and 37 parts per thousand is the most salty it gets when it's been really dry. So the salinity does not vary very much. You add a little bit of water, it may go down to 33 parts per thousand. You take away a little bit of water through evaporation, it may go up to 37 parts per thousand. But salinity tends to stay very constant in the